Hello, everybody. Welcome back to my lecture series for Engineering Sciences 369N, Sustainability Issues and Energy. I hope you've been enjoying these lectures. I've been trying to get them out about once a week, so it's not too burdensome if you're trying to watch all of them. But right now we're in the midst of our unit on carbon dioxide sequestration, or actually CCUS, I guess it is. If you've been enjoying these lecture videos, I encourage you to subscribe to my channel. That way you can enable notifications every time I put up a new video. And yeah, so thanks. Let's get started. So today we're going to talk about subsurface carbon storage. So we've talked about carbon capture, we've talked about carbon utilization. Now we're going to talk about what to do if you just want to, dispose of that carbon dioxide rather than utilizing it for something. Okay, so we're going to do a little thought experiment here. So in April 2022, the atmospheric carbon dioxide concentration was 418.81 parts per million. That's ppm, parts per million. And if you convert this into a mass, this is 3.28 quadrillion kilograms of carbon dioxide. Okay, that's a large number. Now, in all of 2021, the International Energy Agency estimated that the energy-related CO2 emissions were 36.3 billion kilograms. Okay, so that's what is that? 10 to the 5th difference, 100,000 time difference, roughly. So what if we wanted to store either of these two quantities? What if we wanted to just remove the 2021 energy-related emissions? Or what if we wanted to remove all of the carbon dioxide in the atmosphere? Where would we put it? Okay, so let's think about this in a little more detail. So at standard temperature and pressure, which I'm defining as 20 degrees Celsius and 1 atmosphere, excuse me, the density of carbon dioxide is about 1.8 kilograms per cubic meter. So it's about almost 1,000 times, or somewhere between 1,000 to 500 times less dense than water. So if we converted all of that atmospheric CO2, remember that was 3.3 quadrillion kilograms, into a gas at standard temperature and pressure, it would take up 1.78 quadrillion cubic meters. That's a tremendous volume. Same thing, if we just took those 2021 emissions, 36.3 billion kilograms, that would equate to 19.7 billion cubic meters, okay? Now, let's think about where we could put this. So the state of Texas has an area of 696 billion square meters. It's large, obviously the second largest state in the US. So if we wanted to take all that atmospheric CO2 and store it just by dumping it on top of Texas, we would have to cover Texas with a layer of pure carbon dioxide 2.56 kilometers thick. Okay, yes, I'm neglecting compressibility effects here. I'm assuming that through that 2.56 kilometers, the whole thing is at standard temperature and pressure. Okay, this is just a thought experiment, don't at me. Similarly, if we wanted to store just the 2021 energy-related emissions, we could cover the entire state of Texas with a layer of CO2 2.83 centimeters thick. Again, this is neglecting compressibility. Okay, now obviously we're not going to cover the state of Texas with a layer of pure CO2 gas. So we might want to think about some other places that we could put it. So this is a map of the thickness of sedimentary rocks in places around the world. And what I want to point out is that there's a lot of places, if you look at the color scale here, this is colored by thickness in kilometers. So there are some places, particularly the Gulf Coast region of the United States, where you've got upwards of 12 kilometers of sediment. Same thing in some other parts of the world, the area offshore Bangladesh there. So there's, many kilometers thickness of sedimentary rock in a lot of places all over the world. And this rock, it's full of little holes, which we'll talk about in the next lecture. But the IEA estimates that you can store somewhere between 8 and 55 trillion kilograms of CO2 in the little holes in these rocks worldwide. So if we compare that to what we had on the previous slide, so we're talking trillions of kilograms. So this is certainly enough to take up the energy-related emissions for 2021. We're not going to be able to store all the atmospheric CO2 in the subsurface, and maybe we don't actually want to, but we can store a pretty huge amount of CO2 in the subsurface. Now, I mentioned this in, I think, the first lecture of this second unit here. We can actually store a significant amount of CO2 in the ocean because of the solubility of CO2 in water. The Intergovernmental Panel on Climate Change estimates that we can store roughly 1 quadrillion kilograms of CO2 in the ocean. This is approaching the order of magnitude of the amount of CO2 in the atmosphere. There's a bunch of different ways you could do this. You can just inject it as a gas or a liquid phase and let it just dissolve, or you can have it sitting around as these lakes of liquid CO2 at the bottom of the ocean. Liquid CO2 is denser than water. So this is also a possibility. You've obviously got to get the CO2 out there, so this raises some costs, but we're going to focus on geological carbon storage. I'm pretty pessimistic about this type of storage in the ocean. We know that dissolving CO2 in the seawater is going to decrease the pH of the water. This is known to have adverse effects on marine organisms who make their skeletons out of calcium carbonate. There aren't a lot of studies that have been done on what the overall effect of large-scale CO2 storage in the ocean would be on marine life. There may be some species that do better, like algae. I don't know, but we don't know what that effect is going to be. It's one of those things where, like, if you don't know what that button does, don't touch it. That's what I'm always telling my kids. Okay. The other thing here is that dissolved CO2 in the ocean, it has to be at equilibrium with the CO2 in the atmosphere, right? That's just basic, Henry's law. Yeah, right. So if we stored a bunch of CO2 in the ocean, it would have to be at equilibrium with a 550 parts per million CO2 concentration in the atmosphere, which is even higher than it is now. So if your goal is to try to reduce atmospheric CO2 concentration, this is not the way to do it, okay? And then last of all, I'm just really pessimistic that you would get, public buy-in for this sort of thing. So anyway, not to put too fine a point on it, we will focus on geological carbon storage. Okay, this is a phase diagram for carbon dioxide. A phase diagram is a plot, usually with temperature on the x-axis and pressure on the y-axis, and it shows you what different states of matter a particular substance is going to be in at a particular temperature and pressure combination. Okay, so this is the phase diagram for CO2. And you can see there's a number of different phases that are on here that go beyond just solid, liquid, and gas. So obviously we've got the gas region here. So if you're at temperatures and pressures in this region, you'll have gas. If you're above this blue line here, you'll be in the liquid CO2 region. If you're at high pressure and you cross to low temperature, you're going to form a CO2 hydrate, which is something I study a lot of in my day job. And if you're above what's called the critical point, you're actually going to have a supercritical fluid, which is a dense fluid phase that has both gas-like and liquid-like properties. Okay, now what are we going to use this phase diagram for? So let's talk about this in the context of geological storage. So I mentioned to you that rocks are full of holes. We call those holes pores. And so we say the rocks are porous. They have holes. Usually the pores in rocks contain salty water. Occasionally they have oil and gas, but generally it's just salty water. And the pressure inside the pores is usually just due to the pressure of all of the water in the pores sitting above where you are, okay? So you can determine what we call the pore pressure at a given depth D by integrating this equation here. So it's the density of the water integrated with respect to z between surface and your depth. And then that's multiplied by the acceleration due to gravity. This assumes that the water is compressible, so the density is a function of depth. If you assume a constant density, then you can just multiply directly. It's just going to be rho W times G times D, okay? One thing to note is that the expression, the way I wrote it here, this gives you gauge pressure. If you want to use absolute pressure, you just add 1 atmosphere to this, and you're ready to rock and roll. Okay, so like I said, let's assume the water is incompressible. That just makes the math a little easier. So your pore pressure is just rho GD. Now, typical salty water is going to have a density of 1,030 kilograms per cubic meter. So if we multiply rho and G, this gives us a pressure gradient of 10.1 kilopascals per meter, or about 0.447 psi per foot. So that means that we can actually convert this y-axis to an equivalent depth, where if the only source of pressure is just due to the weight of the overlying water, you can convert that to a depth, okay? And so I've converted this to a depth in feet. So you can see 1,600 psi is approximately the pressure we'd have at 3,580 feet depth. Okay, now temperature increases in the subsurface, mainly due to conductive heat transfer of heat transported from the crust mantle boundary due to mantle convection, and then also radioactive decay of various elements in the crust, okay? Now, the rate at which the temperature increases with depth varies a lot by location. We'll see this when we talk about geothermal energy. But if you want to just ballpark number globally, it's about 0.01 degrees Fahrenheit per foot, so 1 degree per 100 feet, or about 18 degrees Celsius per kilometer, okay? Now, your typical surface temperature on land is about 60 degrees Fahrenheit. That's not the surface air temperature, that's the ground temperature just below the surface, okay? So if we convert that to Kelvin, it's 289 Kelvin. So we can actually take that surface temperature and our assumed geothermal gradient, and we can actually make a PT path here on the phase diagram. So that's what I've done here. This is just taking that temperature gradient, using those depth values, and this is approximately what we would expect the pressure and temperature path to be in a normal subsurface environment. So what's interesting is that when we get below a depth of about 2,400 feet, the CO2 is going to be in a supercritical phase. So I mentioned earlier that these fluids exhibit liquid-like and gas-like behavior, but very importantly, they are much denser than gas. And this means that the CO2 in a supercritical phase takes up less space than it would as a gas. So that's a good thing. And just to illustrate that, this is a nice diagram. So if you imagine a balloon filled up with 100 cubic meters of CO2 at standard temperature and pressure, as you traverse that PT path in the subsurface, you can calculate what the density of CO2 does. And you can see that once we get, so, obviously the density increases in the gas phase as the gas gets compressed. When you reach that critical point, then you're in a supercritical fluid. The supercritical fluid is not as compressible as gas. And so you see some density increase, but then it levels off pretty quickly. And when you get to a depth of 2.5 kilometers, which is about 8,200 feet, in the supercritical state, the density is a little over 700 kilograms per cubic meter, which is substantially higher than what we started with. And so that means that your 100 cubic meters of CO2 gas are only going to take up 0.27 cubic meters in the supercritical state. Okay, so that's a tremendous multiplier right there. Now, what's interesting is if you inject your CO2 into rocks that are underneath the ocean. So I'm not talking about injecting it into the ocean. I'm talking about injecting it into rocks under the ocean. Those rocks start at a much lower temperature at the seafloor. Usually in deep water settings, the temperature is something like 3 degrees Celsius. It's very cold in the deep ocean. So if we start at 3 degrees Celsius, and again, do our normal pressure and temperature path, what you see is that we go from the hydrate phase being stable to liquid CO2 being stable. Okay, so it's a little bit different when you're offshore. And then we wouldn't get to the supercritical phase until about 7,000 feet, until about 5,000 feet below the seafloor. So this line that I plotted here, this assumes that your water depth is 2,000 feet. So it's interesting to compare the densities of CO2 both onshore and offshore. So let's do a comparison here. So I'm imagining injection onshore to a depth of 3,500 feet below the surface, and then injection offshore in 2,000 meters of water to a depth of 1,500 feet below the seafloor. So in both cases, we're going down 3,500 feet from the surface, but we have to account for the water depth offshore. Okay, so the pressure, if we're just normally pressured rocks here, the pressure at that depth in both cases is going to be 1,560 psi, which is about 10.8 megapascals. The temperatures are quite different. So onshore at that depth, we're 35.6 degrees Celsius. Offshore, we're 11.4 degrees Celsius, so considerably colder. That means that what's interesting is that because we're at a lower temperature offshore, the density is quite a bit higher than it is onshore. It's 950 kilograms per cubic meter as opposed to 750. So this is just to illustrate that because things are generally colder when you're offshore, you can store more carbon dioxide per unit rock volume offshore than you can onshore, just by virtue of the increase in density. This plot over here, you've probably been looking at it while I've been talking. This is a plot of CO2 density versus temperature. And what we've got plotted on here, these lines are isobars, so lines of constant pressure. And then we've also got the different phases marked on here. So this is gas, this is liquid over here, this is supercritical CO2. And actually, they've got a nice two-phase region plotted on here. We've got gas and liquid at equilibrium. So that's where I'm basing these numbers off of. Okay, so I think I've given you a flavor of where we can store CO2, how much we can store it, and what some of the interesting properties are of CO2 that allow us to store a lot of it in the subsurface. So this is going to be a little bit of a shorter lecture today, but next time we'll start getting into the nitty-gritty of properties of rocks, capillary phenomena, multi-phase flow, all that fun stuff. So I hope you've enjoyed this lecture, and stay tuned for the next one.